Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Central University of Haryana, Department of Physics. Today we are going to discuss about the module Coherent States of Harmonic Oscillator under the paper Quantum Mechanics 1. Learning objectives. So in this module we will learn about the coherent states of a classical harmonic oscillator, the quantum mechanical coherent states. Then we learn about the coherent states as the eigenvectors of the operator. And finally, we learn about the expansion of the states in terms of the harmonic oscillator eigenvectors or the ket vectors. So students, firstly, the properties of the stationary states, that is the eigenvector phi n of the harmonic oscillator, have been studied in the preceding modules. We have seen that the mean values of the position operator x and the momentum operator p of the oscillator are 0 in such a state. It is, however, well known in the classical mechanics that the position x of the and the momentum p are oscillating functions of time, which become 0 only if the energy of the motion is 0. It is therefore expected that the quantum mechanics must yield the same results as classical mechanics in the limiting case when the harmonic oscillator has energy much greater than the quantum h cross omega. In the present module, we shall study to construct such quantum mechanical states leading to physical results which are in conformity with the classical ones, at least for a macroscopic harmonic oscillator. We shall find that these quantum states are coherent linear superposition of all the states phi n described by the eigenvector phi n. These are called the coherent states of the harmonic oscillator. As earlier pointed out, there are many physical situations where the use of harmonic oscillator proves to be an important tool to analyze a wide variety of phenomena. In the domain of quantum optics, for instance, coherent states introduced by Glauber are being currently used quite extensively. Equations of motion. Starting with the classical equations of motion of mass and angular frequency omega, we can write that the equation of motion with respect to position, that is, the time derivative of position as a function of time, is equal to 1 upon mass times the momentum as a function of time. Similarly, the time derivative of the momentum as a function of time, that is d by dt of the momentum as a function of time, is equal to minus mass times omega square times the position as a function of time, xt. Now, in order to perform the corresponding quantum mechanical calculations, that is, if we have to move from these classical equations of motion involving the mass and the angular frequency to the corresponding quantum mechanical equations, then we need to introduce the operators in the dimensionless form. That means that the position and the momentum need to be replaced by their corresponding operators, which are dimensionless. And when we do this, the position operator x as a function of time turns out to be equal to alpha times the position x as a function of time. Similarly, the momentum operator as a function of time turns out to be equal to 1 upon h cross alpha whole times the momentum as a function of time, where alpha is given by under root mass times the angular frequency whole upon h cross, and alpha has the dimension of 1 upon length, so that the position operator as well as the momentum operator turn out to be dimensionless. So we can also see that while alpha has the dimensions of 1 upon length, h cross alpha has the dimensions of momentum. Now, in terms of these quantum mechanical operators of position and momentum, the above classical equations of motion can again be written as time derivative of the position operator xt is equal to omega times the momentum operator pt, and similarly the time derivative of the momentum operator pt turns out to be equal to minus omega times the position operator xt. Motion of oscillator represented by a circle. So just like in classical mechanics, we can represent the motion of an oscillator by a circle. Similarly, here also in quantum mechanics, we can accordingly do the same. So we start with the set of two coupled equations that we have got earlier, and these can be cast into a single equation, which is given as the time derivative of the function beta with respect to time is equal to minus iota times omega times beta as a function of time, where the operator beta as a function of time is equal to 1 upon under root 2 whole times the position operator xt plus iota times the momentum operator pt. And the solution of the above differential equation turns out to be beta as a function of time is equal to beta naught exponential to the power minus iota times omega times t, where the value of the constant beta naught is given as beta naught is equal to beta at time t equal to 0, and this turns out to be equal to, after substituting for t equal to 0 in the above equation for beta, as beta naught is equal to 1 upon under root 2 whole times the position operator x at t equal to 0 plus iota times the momentum operator p at t equal to 0. The time evolution of the state given by the above equation has a simple geometrical interpretation. The state of the harmonic oscillator is represented by the complex number beta as a function of time, which corresponds to a point, say a as a function of time, in the complex plane. The initial position of the point is determined by beta at t equal to 0, whose modulus gives the amplitude of the oscillation, and the time-dependent exponential factor phase determines the instantaneous position of the point, which moves in a circle with angular frequency minus omega. Energy of classical oscillator. Now we note that if we use the classical oscillator, that is the harmonic oscillator, as a circle, then the abscissa and the ordinate of the point A as a function of time, that is the initial point, represent respectively the instantaneous position and the momentum of the harmonic oscillator. The operator x as a function of time is equal to 1 upon under root 2 whole times beta naught times exponential to the power minus iota times omega t plus beta naught star times exponential to the power iota times omega t whole within the bracket. Similarly, the momentum operator can also be expressed in terms of the operator beta, and the value for the momentum operator turns out to be equal to momentum operator as a function of time t or at time t is equal to iota upon under root 2 whole times within bracket beta naught exponential to the power minus iota times omega t minus beta naught star times exponential to the power iota times omega t, where beta naught star is simply the complex conjugate of beta naught, and beta naught gives the value of beta at time t equal to 0. The classical energy of such a harmonic oscillator is constant in time and is given by H is equal to 1 upon twice m whole times momentum at t equal to 0 whole square plus 1 upon 2 whole times mass times omega square times x at t equal to 0 whole square, and this can further be written as H is equal to, that is, the classical energy of the harmonic oscillator is equal to H cross omega by 2 whole times the square of the modulus of the position operator at t equal to 0 plus the square of the modulus of the momentum operator at t equal to 0, and this turns out to be equal to H cross omega times the square of the modulus of beta at t equal to 0. Here it is important to note that the energy of the classical oscillator is much greater than H cross omega, and hence what this means is that the modulus of beta at t equal to 0 is much greater than 1. Quantum mechanical situation. Now let us find out a quantum mechanical state for which the mean value of the operators for position and momentum and the Hamiltonian practically correspond to the values x, that is position, p, that is momentum, and h, that is Hamiltonian, given in the classical case. To define the operators for position, operator x, and the operator for momentum, operator p, in dimensionless form, we had introduced the position operator as being equal to alpha times. We introduce another set of operators corresponding to the position and momentum, where operator capital X is equal to alpha times the position operator x, and this is given by 1 upon under root whole times the operator A plus the operator A dagger, while the operator corresponding to momentum, operator capital P, is equal to 1 upon h cross alpha whole times the momentum operator P, and this turns out to be equal to minus iota upon under root 2 whole times operator A minus operator A dagger. And here basically operator A dagger is the adjoint of the operator A. Also, the Hamiltonian operator H in this new notation is given by operator H is equal to H cross omega whole times within bracket operator A dagger operator A plus half. Now if we consider an arbitrary state represented by the eigenvector psi as a function of time, the time evolution of the matrix element A as a function of time is equal to the expectation value of the eigenvector psi as a function of time with respect to A, that is bra vector psi as a function of time, operator A, ket vector psi as a function of time, and this can be given in terms of the differential equation as iota times h cross times the derivative with respect to time of the matrix element operator A as a function of time, and this is further given as the expectation of the commutator of the operator A and the Hamiltonian operator H as a function of time. Now, substituting for the value of the commutator of the operator A and the Hamiltonian operator H, which is given by H cross omega whole times the commutator of the operator A with operator A dagger times operator A, and this turns out to be equal to H cross omega operator A. The above equation, that is the above differential equation representing the equation of motion, reduces to iota times derivative with respect to time of the matrix element A operator as a function of time is equal to omega times the matrix element A operator whole times as a function of time, and its solution is matrix element operator A as a function of time is equal to matrix element operator A at t equal to 0 whole times exponential to the power minus iota times omega t. The time evolution of the matrix element thus can be given as, for the operator A dagger, as matrix element operator A dagger at time t equal to t is equal to the expectation value of the eigenvector psi t with respect to operator A dagger, that is bra vector psi as a function of time operator A dagger ket vector psi as a function of time. The time evolution equation for the operator A dagger at time t equal to t satisfies the complex conjugate equation matrix element operator A dagger at t equal to t is equal to matrix element operator A dagger at t equal to 0 whole times exponential to the power iota times omega t. If we look at these equations, we find that these equations are analogous to the classical case. Here, the matrix element A dagger at t equal to t can further be written as matrix element A star at t equal to 0 whole times exponential to the power iota times omega t. Now, using these equations that we have got for capital X and capital P corresponding to the position and the momentum operators, we get that the matrix element for the operator capital X at t at time t is equal to 1 upon under root 2 whole times within bracket matrix element A at time t equal to 0 whole times exponential to the power minus iota times omega t plus matrix element A star at time t equal to 0 whole times exponential to the power iota times omega t. Similarly, the operator capital P corresponding to the momentum operator we can also write in terms of its complete matrix elements as the matrix element for operator capital P at time t is equal to minus iota upon under root 2 whole times within brackets matrix element A at time t equal to 0 times exponential to the power minus iota times omega t minus matrix element A star at time t equal to 0 times exponential to the power iota times omega t. Now, when we compare these results with the results that we had obtained earlier, we find that it is necessary and sufficient to set at time t equal to 0 the condition that the matrix element A at time t equal to 0 is equal to beta naught. for all times, where beta naught is the complex parameter that characterizes the classical motion that we are trying to reproduce quantum mechanically. Normalization conditions. Now, we would be discussing the normalization conditions that we can have for solving our harmonic oscillator problem. So, like we have seen earlier, what we are trying to do is firstly to represent the position and the momentum operators as raising and lowering operators, and then to further get the formalism to a point where we can even represent the raising and the lowering operators by a common parameter which we have called beta. So now in this particular section, what we will do is that we will study these normalization conditions with respect to the parameter beta and the generalized lowering or the raising operator A. So the normalized state vector must satisfy the condition, which is that the bra vector psi 0 operator A ket vector psi 0 is equal to beta naught, or in other words, the expectation value of psi 0 with respect to operator A should turn out to be equal to beta naught. We therefore require that the expectation value of the Hamiltonian operator is given by h cross omega, expectation value of the operator A dagger operator A at 0 plus h cross omega by 2 in order to be equal to the classical energy H that is given earlier in the equations. Since for a classical oscillator the modulus of beta naught is much greater than 1, therefore in the above equation, which describes the expectation value of the Hamiltonian operator, we can neglect the term h cross omega by 2 when compared to the term h cross omega times the square of the modulus of beta naught. Thus, as a second condition, we can write the expectation value of the vector eigenvector psi 0 as bra vector psi 0 operator A dagger operator A ket vector psi 0 is equal to the square of the modulus of beta naught, or equivalently the expectation value or the average value of the operators A dagger A at state 0 is equal to the square of the modulus of beta naught. In order to see if these conditions are sufficient to normalize the state vector ket vector psi 0, we consider the coherent states as eigenvectors of the operator A. Eigenvector associated with classical coherent state. Now, let us define the operator B as a function of beta naught as operator B as a function of beta naught is equal to operator A minus beta naught. Thus, using this definition, we have that operator B dagger as a function of beta naught, operator B as a function of beta naught turns out to be equal to operator A dagger times operator A minus beta naught times operator A dagger minus beta naught star times operator A plus beta naught star times beta naught, and the square of the norm of operator B as function of beta naught acting on the lowest state or the ground state eigenvector psi naught, psi 0 is given by bra vector psi 0 operator B dagger as a function of beta naught, operator B as a function of beta naught, ket vector psi 0. And this, using the expression that we have got above, can be rewritten as the norm or the expectation value of the eigenvector psi naught, psi 0, with respect to A dagger A, that is operator A dagger, operator A, minus beta naught times the expectation value of the eigenvector psi 0 with respect to the operator A dagger, minus beta naught star times the expectation value of the operator psi 0 with respect to the operator A, plus beta naught star times beta naught. So basically this equation that we have got has been obtained by simply putting or substituting the value of the operator beta naught, beta dagger, the operator B dagger as a function of beta naught, B as a function of beta naught, which is given by operator A dagger A minus beta naught times operator A dagger minus beta naught star times operator A plus beta naught star times beta naught. So after making all these substitutions and the conditions in this equation, we get finally the expectation value of the eigenvector psi 0 with respect to operator B dagger as a function of beta naught, operator B as a function of beta naught, and this, using the above relation, turns out to be equal to beta naught star beta naught minus beta naught star minus beta naught plus beta naught star beta naught. And since all the terms in this expression cancel out, so we get bra vector psi 0 operator B dagger as a function of beta naught, operator B as a function of beta naught, ket vector psi 0 turns out to be 0. What this means is that the ket vector whose norm is 0 is also 0. That is, if the operator B as a function of beta naught acting on the ket vector psi 0 is equal to 0, or operator A acting on ket vector psi 0 is equal to beta naught times ket vector psi 0. This result shows that the coherent state associated with the classical motion characterized by the parameter beta naught is such that the ket vector psi 0 is the eigenvector of the operator A having the eigenvalue beta naught. Determining the ket vector A. Now, based on the formalism that we have derived earlier, let us now denote the ket vector psi 0 as ket vector A and the eigenvalue corresponding to the operator A by A, so that the final equation that we get is operator A acting on the ket vector A gives us A times ket vector A, where A is the eigenvalue corresponding to the operator A acting on the ket vector A. Thus, if we want to determine the ket vector A, we expand the ket vector A in terms of the harmonic oscillator states ket vector phi n that we have defined earlier. So we can write down this expansion as ket vector A is equal to summation over n Cn times A as a function of A times the ket vector phi n. So now if we want to write the operator A acting on the ket vector A, using the above definition of the ket vector A, we can write down operator A acting on the ket vector A is equal to summation over n Cn as a function of A, operator A acting on ket vector phi n. and this turns out to be equal to summation over n Cn as a function of a whole times under root n times ket vector phi n minus 1. Here it is interesting to note that the operator a is being used as an annihilation operator defined earlier as operator a minus. And if we compare with the earlier equations that we had obtained for the annihilation operators, we find that the function Cn as a function of a turns out to be equal to a to the power n upon under root n factorial this whole times C naught a. And using this relation, we can relate by a recurrence relation in terms of Cn as a function of a, where the recurrence relation is given by Cn plus 1 is equal to a upon under root n plus 1 this whole times Cna. So in this manner, we have got a relation for Cn plus 1a in terms of the function Cna. Thus, we can see that if and when C naught as a function of a is fixed, all the coefficients are known. So we normalize C naught as a function of a so that we can find out Cn as a function of a, and we see that this satisfies the relation summation over n square of the modulus of Cn as a function of a gives us 1. That is, we actually get the normalization condition. Determination of the ket vector a. Now, using all the relations that we have obtained earlier in the equation for Cn as a function of a, rather we finally get the square of the modulus of C naught as a function of a whole times summation over n modulus of a whole to the power 2n upon n factorial is equal to square of the modulus of C naught as a function of a whole times exponential to the power modulus of a square, and this using the normalization condition turns out to be equal to 1. Thus, if we choose appropriately C naught as a function of a to be positive and real, we have C naught as a function of a is equal to exponential to the power minus square of the modulus a by 2. And using this relation, we can finally determine the ket vector a, and the ket vector a is given as exponential to the power minus modulus a whole square by 2 whole times summation over n a to the power n upon under root n factorial times ket vector phi n. So in this manner, we have finally achieved or derived the relation for the ket vector a in terms of the ket vector phi n. So students, now let us summarize what we have learnt in this module. We started with how to characterize the classical equations of motion of a one-dimensional harmonic oscillator to construct the coherent state. Then we went on to know the conditions that are needed to define the quantum mechanical coherent states. After that, we found out the coherent states as the eigenstates of the annihilation operator of the harmonic oscillator. And then we learned how to express the states in terms of the stationary ket states of the harmonic oscillator. So the procedure that we followed in this module was that firstly, we converted our position and momentum vectors to operators. Then further, instead of having these coupled equations involving the position and the momentum operators, we tried to find out these equations in terms of the raising and the lowering operators, and then from there we went on to find out a common operator which could define both the raising as well as the lowering operator, and then from there we then derived our normalization conditions and found out the coherent states, and finally we found out how to express these states in terms of the stationary ket states of the harmonic oscillator. Thank you.